You might have heard about RAG, Retrieval Augmented Generation, using which we can give extra context to LLMs like ChatGPT, Gemini, or any other. The extra context could be anything, our document, files, current news, or anything else. So let me be very honest with you. I completely misunderstood it, or I can say I did not understood it. I knew that what it does, but I did not know was that how it does it. I used to think that the extra context that we are providing in the form of RAG is extending the original LLM, or I also used to think in the other way that the whole context that we are providing in the form of document is being added to our original message that we send to the LLM. But that was wrong. So recently, being curious, I went all in and I started learning about RAG. So finally, I got to know that I was thinking in a wrong direction. Now I'm making this video to clarify how RAG works, because this could happen to any newcomer, and absolutely not because there is no AI content on my channel. Absolutely not. Now let's start from here. I was reading about LangChain and I found this portion in the document that says build RAG agent with LangChain, and it is a very comprehensive document. If you want to ever go and read about RAG on your own, then you can go through this document and read. I read this document and I'm going to use this image as a reference. This image is a very descriptive image of what's going on, so I will use it. But now let's start from the very basics and try to understand what I actually understood it wrong. I used to think that RAG means extending the original LLM and providing the document to the LLM as an extension, but that is not how it works. And I also used to think that any prompt that we are giving to an LLM, we can attach all the documents to the prompt. But practically it is not possible, because we cannot keep extending our prompt and keep adding the document to infinity. So that doesn't work. So if it is not the right way, then what is the right way? How does RAG work? The main thing here to understand is this semantic search. In a normal search, if you search a document, you search it by words or sentences. If it is present, it will return. If not, it will not return. But semantic search is something different. It captures the meaning of the sentence. For example, if I have a sentence called I am exhausted for today in a document, and if I search for I am tired, then it will not return in a normal case. But in a semantic search, it captures the meaning. So since both says that I am tired and I'm exhausted, both means the same thing, the semantic search result will return that sentence even though I did not exactly type tired. So that is how it works, how semantic search works. So for example, this is a large document about OAuth, and here I have a simple prompt, OAuth 2.0 flow. So based on these two words, whatever is matching in this whole large document, it has returned the matching part. Even though the exact word doesn't match, the meaning matched and it returned that sentences. Now that we understand what is semantic search, this is the whole flow of RAG and how it works. We have a store of our document. We will talk about how the documents are stored, but for now, we have a store of our document where we can keep adding our documents later on. When we send a prompt, the prompt is first of all matched semantically with the present documents in our store. If the matching sentences are found, those matching sentences, semantic search results, those matching sentences are appended with our original prompt, and then all together it is sent to our LLM. So this is our original prompt and this is our semantic search. So along with that, our prompt and our context is sent to LLM. So in this case as well, we have our original prompt and some context about it. The both are sent to LLM. So now LLM can better understand what exactly we are talking about. So here we did not exactly send all the documents to LLM, and neither did we extended the original LLM. We just simply used our prompt to semantically search in our documents, and the result appended with prompt is sent to LLM for processing. So that is exactly how a RAG works. Now the last part to understand here is this document. How are this document is stored in a way that allows us to semantically search for our prompts, and that is where this image comes in. So this is the flow of storing our documents in a way that can be used for semantic search. Now let's see the overview of the total flow from document to vector store, and then the vector store can be used for semantic search. Now we have this image as a reference. So we have different kinds of document. It could be PDF, it can be Word document, text file, JSON, or even you can provide URL of some website. For example, this website, it has a lot of text in it which you can provide as a URL, and it will load the documents. Now after the documents are loaded, different types of documents are loaded. These loaded documents are just text, so strings. So these strings are splitted. For example, you say that these are splitted into a chunks of 100 character per chunk. So these total documents are split into various sizes of chunk. For example, 500 character of chunk. So if you have total size of the string is, let's say, 1,000 character, then you split all of them into 200 chunks. So this is splitting. After these texts are splitted, they are embedded. So embedding is nothing but the process of converting those strings into vectors, and vector is a data structure that is used by LLM for semantic search. So you can consider as, for example, you have text which is represented as binary to computers. So to LLM, those texts are converted to vector to derive meaning from it. So you can think of it as a format of storing the string into a form of vector which can be used by LLMs to make sense out of it. So after the embedding is done, these embedding vectors are stored into a vector store. This vector store can be anything. You can use Postgres, PG Vector, or MongoDB, or Chroma. Any database that can store vectors, you can use it to store those vectors. So to give an idea of how this could look, how embeddings can look, I have an image here. So these documents are unstructured data which can be converted into vector representation. So this is a vector. Each row is a vector 1, 2, 3, 4. Now let's see some code and actual implementation of this flow from document to vector to get the practical view of what's going on. Here I have a very simple Python code which converts the documents into text embeddings. So it is divided into blocks for easier understanding. Let's start with this simple block. This block is nothing but reading a file and loading it in the memory. So that's very simple. So this document is this file that I showed earlier in the example. So we are reading this file and just printing the first 500 character from this document. So as you can see, these are the first 500 character. So if I change this to, let's say, 600, then it will print the next 600 characters here. After we have loaded the document, this is our text file, string file. So we will continue, and in the next step we will do chunking. So we will convert the total string into chunks of size 1000 characters. So we are saying that take the total document, split it into 1000 sized chunks, and then an overlap of 200 characters. So for example, in this 1000 character, the first 800 will be unique and the next 200 will overlap with the next chunk. So visually, for example, these are 5 chunk, then the last 200 character of this chunk will be similar to the first 200 characters of the second chunk. So that's what happening here. Now we take that text from the above code, this text, and then provide it to this function which splits the text and prints it. So now I'm just printing the length of this splitted text. So we have splitted our total documents into 1000 character, which makes up to 213 total chunks. Now we have the chunks. This is text splitted chunks. Now what we can do, next thing, we want to embed, and then that means we want to convert the text into vector. So as I said, we will use a model that can convert our text into embedding. So this is the model. You can use any model out there. I'm using all MNet base v2, but you can use any model to convert your text into embedding. That doesn't matter. So we have this embedding here, and in the next step we are using Chroma. It is a local database, I could say. It uses the embedding and it stores the embeddings in your local file, as you can see here. So it takes the embedding functions here and provide it to Chroma. It will create a new collection. It will use this embedding model and then convert the text into embedding. So here we are using vector store.add documents, and document is the text splitted. So we are providing the splitted text here, which is going to this embedding function. After the embedding is done, it is stored in Chroma. So these two blocks are used to convert the text into embedding and store into Chroma database, which is present here in our local DB. After it is done, now we can search from the database. So this last step is nothing but searching in the database. So I'm saying that search for something like OAuth to flow in the database and also provide me what is the matching score. So for example, if I change this to what is OAuth 2, then again it will show a different result. Now let me run it And as you can see, based on this string, it searched the database and found the similarity score and what is similar and returned that text. So as you can see, the similarity is 0.6, and these are the text content that is similar to what I have provided. So in the similar way, we now take this context and our original prompt and then provide it to LLM. So this is the flow of how the RAG works. I hope you understand the whole flow and now you are not confused about how RAG works. So I will see you in the next one. Keep watching.